So far in this unit, we've talked about how to measure the rate of a reaction. Reactions don't always happen at the same speed. Every reaction has its own rate, but there are also things we can do to change the rate. We can change the concentration, we can change the surface area, temperature, or we could add a catalyst or sometimes an inhibitor. Let's look at each of these by themselves. Each reaction happens at its own rate. Some are really fast, some are really slow. There's different sized molecules. Some of the molecules just are more easily combine. Other ones, it's really difficult for the reaction to actually occur. And we've looked at these graphs before, these graphs with reactants and products, and we've compared the enthalpy by figuring out the difference between reactants and products and calculating that. But what we didn't talk about is this lump right here. That lump right there tells us how much energy has to be added into a reaction for it to actually occur. And if that lump is larger, that means that that reaction would take more energy to happen. If a reaction had a lower lump, a lower activation energy, that means it would take less energy for the reaction to occur. So that's one of the reasons that all different reactions happen at different rates. The reactions that need more energy are going to happen slower because it is more difficult for a reaction to take place if the molecules have to have more energy for the reaction to happen. If a reaction requires less energy to occur, it's going to happen more quickly. More molecules will have that much energy, so more of them will actually react. Concentration is the first way we can change the rate of a chemical reaction. In a chemical situation that has a lower concentration, what we're looking at is fewer molecules of the chemical in the particular volume. If we're looking at something that's more concentrated, there are going to be more molecules of the chemical in that volume. In this image on the left here, that's lower concentration, we have 11 dots representing chemical. The rest of the container is made up of water. On the right side, it says more concentrated. We have 20 dots, and the rest is made up of water. So the one on the left is going to happen a lot slower because we are going to have fewer molecules that are going to be bumping into the other chemical. Most of the time that this is colliding, it's going to be collisions of water molecules with the chemical, and fewer of the collisions are going to be from chemicals that are involved in the reaction. In a more concentrated chemical, there are a larger number of molecules per milliliter, which means when all those molecules are bumping around and colliding with each other, many more of the collisions are going to be from the actual reactants, and not as many are going to be from water. So in the more concentrated situation, you're going to have more collisions between the two reactants involved, and when there are more collisions, that means the reaction is going to be faster. Low concentration, you have fewer collisions per second because more of the collisions that are happening are between water and the reactant, and fewer of them are between the two reactants involved. More concentrated, you have more collisions between the two reactants involved because there are more of these little dots, more of the chemicals in the same volume of liquid. The next way we can change the rate of a reaction is by changing the surface area of one of the reactants. Surface area is the total amount of area that the outside of the chemical chunks take up. Something like on the left side where you have one large chunk of chemical, if we just add up the amount of area that the outside represents, it's smaller than it would be if we had each individual little piece broken up into separate parts there. The total amount of chemical is the same, but on the small surface area, fewer molecules are available for the reaction because the rest are trapped inside. Now, if you break up the chemical into smaller pieces, like this, if you look at the outer edges of these things here, there is a lot more total area made up by these smaller pieces. So if you crush a tablet, or if you chop it in little tiny bits, or anything like that, you end up increasing the surface area. And when you increase the surface area, more parts of the chemical, more of the molecules are exposed to the other reactant at the same time. So when you have a large surface area, there are more collisions per second, which means there's a faster reaction, simply because there are more exposed or accessible molecules to react. Temperature has a dramatic impact on the reaction rate. When you have slow molecules, like over on the left side, the molecules move very slowly, collide infrequently with the other chemical, and the collisions that do happen have less energy. If they have less energy, they're less likely to be successful. They're more often just going to bounce off of the other reactant with no effect. So low temperature, slow molecules, few collisions, fewer successful collisions, and overall a very slow reaction. On the right side, we have the higher temperature molecules. We have these molecules just flying around like crazy, rapidly colliding with the other reactant. When they do collide, they have more energy, they're more likely to successfully react, and therefore, with more collisions and more successful collisions, because of the more energy, there's going to be a much faster reaction rate. The last way we have of changing the reaction rate are catalysts and inhibitors. A catalyst is going to be changing what the activation energy of the reaction is. In this situation, the activation of the catalyzed system is shown in the dotted lines, and the uncatalyzed, the regular one, is here with the solid line. And you can tell by looking at this that the activation energy of a catalyzed reaction is far lower than the activation energy of the uncatalyzed reaction. So what the catalyst does for you is makes it so that more molecules have enough energy for the reaction to occur, whereas if it's uncatalyzed, fewer molecules have all the energy to make it over that bump and have a successful collision that will cause a reaction. So catalysts speed up reactions by reducing the activation energy. Inhibitors are less common, and what they do is they increase the activation energy even further than what it normally would be. So they slow down the reaction by making it more difficult for the reaction to happen. Fewer reactants will have the energy to do that, so the reaction is going to slow down. One important thing about a catalyst and inhibitor, though, is that it doesn't overall change the enthalpy of the reaction. That's going to be the same no matter what. With a catalyzed pathway, it's easier for the reaction to start, but the overall change in energy is exactly the same as it would be if it was not catalyzed. Inhibitors, too, they slow it down by making it even more difficult to react, but it still has the same enthalpy. The change in energy from beginning to end is still exactly the same.